Hi everyone. Today we're going to be looking at section 5.2, which is a discrete probability distribution known as the binomial probability distribution. Binomial is right there in the title, but it's really just a discrete probability distribution. Remember, discrete just means they're the things that you count. So in all of these problems, we're just going to be counting the number of times something happens. The number of times that we're counting that it happens is what we refer to as the success. Okay, so this is similar before we even look at any of this stuff down here. It's just like if I said I'm going to flip a coin 12 times and count the number of times I get tails out of the 12 times. That is a binomial experiment, also known as a Bernoulli trial. So the probability of a binomial experiment can be calculated when you have the following four conditions met. These four conditions are known as Bernoulli trials, and the first condition says you have to have a fixed number of trials, which is always n. Use lowercase n for that. And that just tells you you're going to do something. In my example, I said 12 times. The n trials have to be independent, meaning that the outcome of one does not affect the outcome of the other. And number three, there are only two possible outcomes for each trial, meaning you could get either heads or tails. That might be you're counting something else happening, like the number of people who like dogs, or they don't like dogs, or they ate dinner out last night, or they did not eat dinner out last night. Things that are kind of yes or no questions. So the fourth thing is that the probability of a success does not change from trial to trial, meaning if you pick a different person, or it's like 10 minutes later or something, it doesn't make any difference. You still have the same probability all the way throughout. Okay. If we know we have a binomial experiment, we have to check these four things. Some of the things that I usually will ask on a quiz or on a test would be, explain why something is a binomial experiment. So explaining why something is a binomial experiment just involves making sure that all four of these things are met. Okay, so if we look at these two examples here, I said you could toss a coin, in this case, 10 times and find the probability of getting two heads. Okay, well, that's a probability experiment based on binomial, because when you flip a coin, you've got the fixed number of trials is 10. Coin tosses are independent of each other. It's always 50-50, so the probability of a success does not change, and there's always two outcomes. Okay, this second part right here, if you question 20 people in class and look for the probability of more than half of them being women, well, okay, is that binomial? Well, there's 20 people in class. What's the chances? If there's 20 people, that's the fixed number of trials. Are they independent? I assume that gender is independent. It's if the person standing next to you is female, it doesn't make it more likely that you are female. It's just they're just independent. Are there two outcomes? Female or not, basically. And then probability of success, is that changing? Person to person? No, it's about 50% chance for anybody. So that also is a binomial experiment. And then shooting 5 arrows at a target, if you count the number of times you hit the target, that also is a binomial experiment. Okay, this next part in the reading is just deriving where the formula comes from, and it comes from using the multiplication rule. And I would encourage you to look through that, but we don't really need it in order to do the problems because we're going to end up using technology. One of the things that I would say, though, is that when you look at this, if you do look at it, it has to do with using both the multiplication rule and the addition rule combined, is how this comes up. Okay, and I'm not going to go too much into that. I'm going to scroll down here and look at this part. Okay, so these are the notations that we use when we talk about a binomial experiment. N, that's the fixed number of trials. Lowercase p is the probability that you have a success in any one trial. So that would be like 50% chance that you get tails when you flip the coin. The specific number of successes in the n trials is x. That's what we're counting, how many things actually occur, the quote successes. And then p of x is the probability of getting exactly x successes, again, the thing we count in the n trials. And then there's this formula here, and this is what they were derived up above in the reading. This awesome formula, and this formula is great right here. It's an awesome formula to use, but it's really only going to be useful if you're calculating probability by hand. Otherwise, we use StatCrunch, or you could use a calculator, or you can use a probability app. I've made a list in the reading of probability apps you can put on your phone. If accessing StatCrunch is difficult, if you don't have access to a computer with StatCrunch, then you can download one of these probability apps and do basically the same thing. Okay, so here's the technology. This part of the section tells you how to do it, how to input things. Okay, these right here are the iOS versions for iPhone and iPad, and then this is an Android version of a probability app that I've used for the last couple of semesters that's free and that you can use. So it's kind of nice. All right, let's go to a problem. Okay, so this is the first example. When looking at a person's eye color, it turns out that 1% of people in the world have green eyes. I didn't know that, but that's something that's in this problem. So now we want to consider a group of 20 randomly selected people. So the first step is explain why this is a binomial experiment. Okay, well they didn't tell us what we're counting, so I'm going to assume in the problem that we're going to count the number of people that have green eyes out of 20. So let's check to make sure this all works. So 1, there are 20 people, which is each person is an independent trial, so there are a fixed number of trials with n equals 20. So check. Step 1, we're good. Okay. 2, if we assume that every person in the group is chosen at random, then the eye color of one person doesn't alter or affect or have any impact on the eye color of the next person that we would randomly choose. So the trials are independent. 3, there's 2 outcomes, right? Either you got green eyes or you don't. You notice we're not counting green eyes and blue eyes and brown eyes because that's 3 different outcomes. We're counting these 2 outcomes as you have green eyes or you don't, and that's all we're thinking about. And then state the random variable. Okay, random variable is x, the number of people with green eyes out of 20. And now we get to the probabilities. We want to find the probability that none have green eyes. And this is what it will look like on the computer. Then we're going to find the probability that 9 have green eyes. Then we're going to find the probability that at most 3 have green eyes. Okay, so I'm going to open up StatCrunch here. Bear with me for just 1 second. StatCrunch. All right, so I go to Stat, Calculators, and Binomial. And this is what always pops up when you start. It's just this nice little almost bell-shaped looking curve here. All right, so now I want to have n equals 20. We had 20 people, and the probability of having green eyes was a 1% chance. So I'm going to put in p as 0.01. And the first question we were going to ask is, what's the probability of having nobody with green eyes? If we click compute, the probability of having nobody with green eyes is equal to 0.8179. So it's a pretty likely scenario, right? Because if only 1% of people have green eyes, it's likely you're not going to have very many people with green eyes. And so having nobody with green eyes is a fairly high probability. All right, so that's the first part. Now, if I wanted to know 9, I think was the second equation, I just change, whoops, I don't want to change n is 20. I want to change the probability that x is equal to 9. Click compute. And this says 1.5 something or other, and there's this e to the negative 13th power. That means it's scientific notation, and we're going to have to take the decimal, which is sitting right here between the 1 and the 5, and move it 13 places to the left. So it's going to be 0.0000000000000. Maybe that was 12 zeros, I don't know. Then a 1, 5, but it's a lot of zeros and 1, 5. So it's not likely you're going to see 9 people with green eyes. Just is not likely. And I think the last question was at most 3. At most 3 means you could be 3 or 2, or you could be 1, or you could be 0. So we're going to say at most 3, change the 9 to a 3, and at most 3 is the same as less than or equal to 3, and then we compute that, and it's 0.999957. So it's highly likely that you would have at most 3 people that had green eyes in this binomial experiment. All right, well that's pretty much the the view of what we're going to have here in this. We're up to the homework, and I hope that that helps, and I hope that everything is going well. All right, thanks a lot. Bye-bye.